Hello, my name is Christian,
My name is Patricia.
and we want to talk about the principal direction and components, and the eigenvalue problem, and lastly the Mohr circle. Yeah. Okay, so we all know that stresses they are directional, so therefore it's important for engineers to be able to locate the direction of where the largest stress components are present, either the shear or normal stresses. And the direction where the largest normal stress components are and where the shear stress components they vanish is called the principal direction. And what we're going to talk about is the transformation of a plane stress state. Then we're going to talk about the principal stresses, then the eigenvalue problem, and last the Mohr circle in both 2 and 3D. Okay, so to arrive at a formulation for the principal stresses, we first have to describe the transformation of stress components. And we're looking at a plane stress state. And I mean, the transformation associated with the 2D case or plane stress case are rotation. So we consider here a x, y coordinate system, and then a new coordinate system x prime, y prime, which is rotated at an angle theta. And if we look to the right, here it shows the stress component associated with these two coordinate systems. So we have sort of like rotated, we've done a rotation, but it still describes the same stress state, just rotated. Okay, so to describe the new coordinate system, we define two orthogonal basis vectors, x in x prime and in y prime, which is defined this way. And it's convenient to set up in what is called a coordinate transformation matrix for the 2D plane case, which is shown down here. And the transformed stress components are then calculated as the following matrix multiplication, where sigma holds the stresses in the x, y coordinate system and x prime in the new rotated coordinate system. And to elaborate this matrix multiplication, we first have to consider the sigma times the A. And what we get here is the stress components on the rotated surfaces, so here, but it's still explained with respect or expressed with respect to the old coordinate system. So to get them expressed with respect to the new coordinate system, we have to multiply the transposed A matrix in front. And it turns out that this matrix multiplication yields the following two normal stresses here, or the transformed stress components. It yields the normal stresses here and the shear stress component down here. And with this result, we can actually describe the entire stress state in any direction. Okay, so the principal coordinate system. And again, as said previously, this is the coordinate system where the shear stress component they vanish. And obviously here we also have the largest normal stresses. And again, we consider the same, the rotation of the coordinate system. But now you see in the rotated case, there are no shear stresses. Okay, so what we do is that we consider the transformed stress components as just found previously. And what we do is that we take the shear component term down here, set it equal to 0, and solve for the angle theta. So we sort of find the angle which defines the principal direction or coordinate system. And it yields this expression. And when we put the angle theta into the normal stresses, we'll end up with the principal stresses. Okay, so an alternative way to find the principal stresses are to consider or solve the eigenvalue problem, which is seen here. And how to interpret this is that we are going to solve for eigenvectors v, which represents the new basis or the eigenbasis, or sort of like the coordinates. They define the coordinate system in the principal direction, where v is the eigenvectors and gamma is the eigenvalue. So when we introduce the identity matrix I, we can rewrite or rearrange the equation like this. And to only get non-trivial solutions, we'll solve for the determinant equal to 0. And what we end up with, working out the determinant of the matrix in here, is that we get a quadratic equation. In this 2D case, we'll have two solutions. And it turns out that these solutions, or the eigenvalues, it turns out to be actually the principal stresses. And sort of like to take the analogy which I just mentioned to the transformation of the coordinate system, is that if we were to solve the eigenvectors in this 2D case, v1 and v2, it'll actually be in x prime and in y prime with the principal angle. So we are in the principal coordinate system. So if we do the exact same matrix multiplication or the transformation, we'll just end up with a new matrix which holds the principal stresses in the diagonal.
So now I'm gonna talk about the Mohr circle. Mohr was a German engineer. He basically realized that when you write the equations to transform the stress by rotating the stress elements, you get equations that look like a circle, the equations of a circle. So basically here you have the stress state, sigma xx, sigma yy, and sigma xy. And then he realized that the circle is the location of points that represent the stress states on individual planes at all their orientations. So basically, no matter how you rotate the Mohr circle will give you the stress state. So here you have the principal stresses in the figure, and then you rotate the plane by theta, and you get these principal stresses. And here you have the transformation equations. When you apply the principal stresses and the transformation equations, you get these new equations. And here you have the Mohr circle. So basically the shear stress on the y face must be equal and opposite to the shear stress on the x face, so you can get a static equilibrium. The shear stress x with positive downwards, it's better to do this way because it makes it simpler for us, because you get a 2 theta angle here, and then if the positive is downwards, the orientation of this 2 theta will be the same orientation that you rotate the circle. So it makes it simpler for us if you put the positive downwards. And here you have the parameters after you build the circle. You have the center, sigma x plus sigma y divided by 2. You get the center, who is also called the sigma average. You have the radius that you have here, but like when you have principal stresses, the shear stress is 0, and then you have exactly this equation. They are basically the same. And then you can find the shear stress, the maximum shear stress, which is equal of the radius, but it'll be fine up here in the Mohr circle. The Mohr circle can also be found by for triaxial stress. It's basically the same analysis that we did before in the plane stress, but now we do the same analysis 3 times. So basically we rotate the element around the c-axis, and then you can analyze the plane AB as a plane stress. So the shear stress perpendicular to the c-axis is 0, so basically the shear stress in the A phase and the B phase here, it will be 0, which will give us a principal stress. And the sigma c here is perpendicular to plane AB, where our analysis is made, and does not affect the transformation. Then you're going to rotate the element around the a-axis, and then you have the same analysis, and then you rotate the element around the b-axis, and you do the same analysis, and then you've got 3 circles now, because instead of doing the analysis 1 time, you did it 3 times, so it gives you 3 circles. Okay, so the circle of diameter AB determines the normal and shearing stress on the face when the element is rotated about the c-axis. And then the element of diameter BC determines the same thing when it rotates around the a-axis, and the element, the circle of diameter AC, determines the same thing, but when the element is rotated around the b-axis. So basically, we could do the rotation with any axis, and it would lead us to stresses represented inside the like shaded area, the hatched area in orange. So that's why the Mohr circle helps us to visualize what we are doing, and it makes it so much simpler. And thank you for your attention.
Thank
That's
you.
it.